So, chapter one is really concerned with critical thinking, problem solving, things of that nature. That's going to be what's really important to us in chapter one. And what we're going to find is that really kind of means word problems. Of course, we have dealt with some word problems before, but the nice thing is we're going to introduce something called the Polya's four-step process or problem solving process. And you don't have to write this down verbatim. The first step in the Polya's process. So you're given a problem, you're given a math problem, you're given a word problem, something that right on the surface, you're not immediately ready to start solving it and figuring it out. You really need to understand the problem to start with. Read it a couple times. Just your first reading, don't jump in assuming you have to understand everything immediately the first read through. Give yourself a little time, especially if you're not on an exam. If you're on an exam, you have to be a little more judicious with your time. A major part of this is to read the instructions carefully. If you're on an exam, if you were doing it by paper, or even if you're on an exam that's digital, you really, really want to make sure you read all of the instructions carefully. And I mean that. That's huge because so many times I'll grade exams and a student will get something wrong because they did the wrong thing because they didn't know what they were supposed to be doing. They thought it was one thing and it was not. So that's something I would add into this little step here. And then finally, in your second reading, write down what information is given. Use shorthand. If it's simpler, if you can write it in less words, if you can write it using some mathematical symbols and the like, get that down there. The major part of this is determine what you're looking for. What are you trying to find? What are you solving for? What is the purpose of this? Your next step in the Polya's process, and again, you don't need to write all this down. You want to devise a plan. So you might use inductive reasoning to look for a pattern. Remember, inductive reasoning makes a probability argument or draws a probability-based conclusion, which means patterns are generally a staple of inductive reasoning. Make a systematic list or table, sure. Make it, estimation though is the best one. Use estimation to guess what the solution could be. If we're working chapter 8 problems and we are doing, say, a tax problem, where we're calculating how much income tax someone owes the government. Well, if someone made $60,000 last year and they do their income tax calculation just based on last year's income, and they realize they owe the government $500,000, there's probably a mistake made somewhere. So if someone's making $60,000 a year, they probably will owe anywhere from 15 to 25% of their income in taxes. So, that could be anywhere from $9,000 to $15,000. That's the ballpark you're looking for. But people's situation can vary. Some people can make that much money and owe $0 in income tax. If they have children they're supporting, if they get other certain types of tax credits and deductions they can take. But just make a ballpark guess. Look at the problem carefully. If you're buying a house that's a $200,000 home, your monthly payment is probably not going to be in the millions of dollars or negative. It doesn't make sense. So, you can do other things. You can sketch or diagram your problem. That's a pretty popular technique. Especially when you get to certain math problems that involve shapes, that involve geometry, things like that. You're calculating area, perimeter. You're just going to want to draw a picture. There's just no two ways about it. I do it still to this day, every time. I don't skip on that because I've learned you take a little bit of time at the beginning, you dot your I's, cross your T's. It's going to save you a lot of pain in the back end of working a problem. Step 3, which should be the hardest step, gets the least amount of love here. It's just carry out the plan and solve the problem. You've devised a plan. You figured out, I need to set up an equation. All equations are naturally going to have at least one variable involved. Here's the possible variables. Here's what they stand for. Bada bing, bada boom. That's a kind of a plan you're working on. And then finally, when you have gotten an answer, go back and make sure it satisfies the conditions of the problem. Make sure it's a sufficient answer. It makes sense. If it's an equation you're solving, you could plug it back into the original equation. Make sure it is indeed a solution to that equation. But there's all kinds of other tricks you can do to determine if your answer makes sense. Look at your answer. Again, if you were making $1 million monthly payment to buy a $200,000 home, you've made a mistake, because that would be an exorbitant interest rate. That would be an absurd, obscene interest rate. So we can kind of work through these problems a little bit. A lot of them are just going to be word problems where we apply this Polyaz four-step process. So a man purchased 5 shirts, each at the same discounted price. How much did he pay for them? Did we miss something here? Let's see. So if you're working this problem now, it looks like this is not a complete problem. But you could still maybe set something up here. You know you've purchased, the person's purchased 5 shirts. You then kind of look over this. The discount of each shirt is not giving. Oh, look, the missing piece of information makes it impossible to solve the problem. If you want to know how much in total he spent, you need to know how much each shirt costs. Yeah, there's nothing given to you here to solve this problem. So when you're working through the Polyaz four-step method here, you're going to pretty quickly run into a wall and be like, what the heck am I even setting up? There's no equation because I don't have enough information. There might be some tricksy homework problems where they try to get you to solve something that's you can't solve because it's inane. There's not enough information. So there will be an option though. They'll be like, there's not enough information to solve this problem. That's a popular choice to just select that one. Like you look at a really hard problem and you just say, there's not enough information. And usually you're actually going to be wrong. There's more than enough information. You just don't know how to solve it. Okay, let's look at another one. By paying $100 cash up front and then paying $20 a week, paying off the balance at $20 a week, how long will it take to pay for a bicycle costing $680? Well, my gut is telling me this is assuming no interest. This is assuming that you're not charging any interest, whoever you're buying it from, which is almost never going to be the case. That's almost never going to be the case. They're pretty much always going to charge interest on you, whether you like it or not. But you can perhaps assume there's no interest. Okay, so you have the cost of the bicycle. You're paying $100 up front, $20 weekly payments. Well, what you would clearly need to do is you would need to know, hey, how much am I actually going to be having to pay back? So out of $680, you paid off $100, you still owe $580 on the bicycle. If I'm paying $20 per week, I need to divide the remaining $580 by 20, and it's clear I'm going to end up with 29 weeks. 29 weeks. And that's the answer to it. You're going to be paying off this bike for over half a year, $20 a week. Maybe that's doable. Of course, it's awfully generous. Whoever, they're just letting you pay at no interest. Maybe that's layaway. And layaway, they usually don't charge interest. Layaway just means they'll reserve the item for you. No one else can try and buy it from under you. And they'll give you till a certain date to pay it off. And as long as you pay it off by that date, then you can come get the item. But the whole point of layaway is that they protect it for you so no one else can come sneak it from you. So that's a pretty popular option during Christmas. They'll usually, but you can't get the item until you pay it off. So that's how they keep you from just, stiffing them for the money. Now all we need to do is double check our answer, say, okay, well, 29 weeks. If we're making payments of $20 for 29 weeks, that's 500 in total, 580 in total amount of weekly payments. And then if we add on the $100 we paid in cash, yeah, that does indeed get us back to the $680 exactly that we needed to pay off the bike. So the Polyaz four-step process, pretty straightforward. There is some homework over chapter 1 here. But again, it's pretty straightforward. You are an engineer programming the automatic gate for a 50-cent toll. It only allows the wrapper 50 cents to go through the toll. That's not true. The gate accepts. Oh, wait, what? No, it'll let anyone through, but you got to pay 50 cents. I wish tolls were only 50 cents. That's like one exit off the George Bush or something. The gate accepts exact change only and does not accept pennies. How many coin combinations must you program the gate to accept? Well, it won't take pennies. That means it'll take nickels, dimes, quarters, and it only takes exact change, so it won't take dollar bills. You have to put, certain things. And then I guess it's including half dollars. I don't think I've ever held a half dollar in my hand. It's a 50-cent piece, but I assume they exist, I would imagine. So we need to find different ways we can combine half dollars. Well, just a single half dollar will do it. But then you could do 2 quarters. That's another combination that'll do it. So you need to start thinking, what are the ways I can add up some of these different coin amounts, however many I need of them, in order to get to 50 cents. So maybe our plan on this one is going to be, well, make a list of all the possible coin combinations. Just start with the basics and start generating them in your mind. Okay, a single 50-cent piece, done. 2 quarters, done. 5 dimes, done. 10 nickels, done. But then start combining, mixing and matching different amounts of each together. 3 dimes, and so that's 30 cents, so 4 nickels. 3 dimes and 4 nickels will do it. Those are the kinds of things that we're wanting to generate with this problem. So let's make a simple table. Each row of the table is going to be a single combination. So 1 half dollar, and then you don't need anything else here. That'll cover it. 2 quarters, that'll cover it. 1 quarter, 2 dimes, and 1 nickel. That'll cover it because you get 25 cents from your dimes and nickels. 1 quarter, 1 dime, and 3 nickels. That'll take care of it, Pilgrim. So you start with the highest amount, the highest face value coin, and you can just kind of go down the line here. And you can see, ooh, okay, 4 dimes, 2 nickels, 3 dimes, 4 nickels, 2 dimes, 6 nickels, 1 dime, 8 nickels, no dimes, and 10 nickels. And actually, it looks like this is a pretty exhaustive list. We're not allowing pennies. Pennies are evil. There was a time in the 80s when pennies they used copper. They, printed pennies with copper. They're made of copper. And literally the amount of copper that was used in a single penny was worth more than 1 cent. It was worth more than the actual penny's value, which created problems. So they've actually changed it to a cheaper metal that's easier to make. So let's count. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 11 different change combinations you can do. That's change I can believe in. So the answer here would be 11. The only way to really check this one is to just go back and make sure you're not missing a single combination. But it looks like they used some nice deduction here. Just try to, maybe you can test it by mentally saying, okay, 1 dime is 10 cents. I need 40 cents more. That's 8 nickels. But, oh, wait, I've already got that on here. You can kind of go through the list that way. So that's another kind of problem. So we're just kind of looking at Polyaz method. 4 runners are in a 1-mile race. Maria, Aretha, Thelma, and they missed a huge opportunity to say this last person was Louise, but I guess it's Debbie. So these 4 people, points are awarded only to the women finishing first or second. The first place winner gets more points than the second place winner. I cannot speak today. How many different arrangements of first and second place winners are possible? So this is actually a really interesting question. We're going to study this briefly towards the end of the semester, probably all the way into January. It's not January, December. We're going to study this pretty late on, and we're going to learn that this is actually a permutation of 4 objects taken 2 at a time, 4p2. So that's really cool. All right, so there's a couple different possibilities. Let's think, who could go in first place? Oh, Maria could go in first place. But then there's 4 different people, but we're just pretending like Maria is set in first place. But then there's 3 other people who could take second place: Aretha, Thelma, and Debbie. So this creates 3 possibilities right off the bat: Maria and Aretha, Maria and Thelma, Maria and Debbie. But now we can extend that and put 4 different women into the first place slot. Aretha can go first, then Maria second. And notice Aretha Maria is not the same as Maria Aretha, because first and second place are different from each other. So even though it's the same 2 women in the top 2 spots, you can have them finish one way or another way. So there are 2 different ways that can happen. That's actually the principal difference between what is called a combination and a permutation that, again, we will study later on in the semester. So Maria Aretha, Aretha Maria. But now you can see there's 12 total possibilities. And using this little tree diagram is actually pretty neat. This is called a tree diagram. It's also called a stochastic process, because later events or later pieces of the tree depend on the outcome of previous places. That's what a stochastic process is. So there's 12 possibilities here. There are 12 possible combinations. There's actually another way we could do this one, and this one's just for fun. We're going to say that there's 2 places here. You can place in first, or you can place in second. Now, there's 4 women that could make that first place, and I've already forgotten their names, but there are 4 of them. Now, once you've chosen one of those 4 women and selected them for that first place slot, now there's only 3 left who can take second place after the first woman has taken first place. And you're going to multiply them. And the reason we multiply them, maybe that picture we just looked at with the different things might actually be helpful here. Think about this original picture we had with the tree diagrams. You're going to have 4 different groups. It's 4 groups because there's 4 women. You're going to have 4 different groups of 3 because there's 3 women that can then double with them. So it's 4 groups of 3, which is another way of saying 4 times 3, which is just 12. And so that's actually why we multiply. You're not really sure why, but you want to multiply, to quote Limp Bizkit. You're going to multiply there and get 12. Why don't we add them? Why don't we subtract them, divide them? That's actually not a bad question. We're going to learn something called the multiplication principle for counting. It's one of our basic counting techniques, whether you're counting crows or any other kinds of objects. And we're going to see we'd actually want to multiply those 2 numbers in that particular case. So either way, all roads lead to Rome, all roads lead to 12. Okay, real quick, I want to talk about calculators. Because as some of you know, you are allowed the use of a calculator for the second half of this course. You are allowed to use a calculator. Let's see, here we go. There's going to be, you can technically use any calculator that is a scientific calculator or better. Scientific calculator or better. You can write that down. That means you can use a graphing calculator. We're actually not, you might need it very briefly for some of the chapter 1 material. So technically your first exam, I will allow you to use a calculator, but you're going to see that the next 2 chapters, chapters 2 and 3 that we cover, really you're not going to need a calculator for those. But then we hit chapter 8, we skip over some chapters in our book. We hit chapter 8 and you definitely need a calculator for the rest of the course for going forward. So let's look at the two principal types. Technically, you can use any calculator that's scientific or better. I'm fine with that. But let me show you the best two calculators. This is called the TI-30X2S. This is just a Google image search of it. Looks like you can go to Amazon. But I don't want to click it because I don't want you guys to see my recent Amazon purchases. It's all Halloween stuff. But I want you to be like, Josh spent $25,000 on Halloween decorations this year. I was like, well, I wish. No, I don't have 25 grand for Halloween decorations. Anywho, this is a TI-30X2S. It looks like this. You've probably seen this. You might already even own one of these calculators. This calculator is perfectly fine. I bet you it's $15 or so on Amazon, which is pretty amazing. And you can get it at our bookstore here at Weatherford College. You can get it probably if you just walk into a Walmart or a Target. You can get it at one of those two places as well. I'm pretty sure that these calculators are used as currency in some countries because they're so common. You see them everywhere. So this is the TI-30X2S. This is kind of the standard scientific calculator out there right now. It's the most common one, at least. This is a perfectly acceptable calculator, and I would suggest using this one if you just want to use a scientific calculator, and it will do everything you need, period. It'll do every single calculation we need for this course. The other kind, you can use a graphing calculator. Let's see if we can get a good picture of one. Yeah, this is the TI-83 and 84 series. They're secretly rough. They're practically the exact same calculator here. The 84 is just a little bit beefier. It looks a little newer. This kind of looks like it's from the 80s, but don't you sleep on that TI-83 Plus. That thing will do more than your wildest dreams. This thing is an incredibly powerful calculator just because it was made in like the 90s. It's still an awesome calculator today. The 84 is just kind of like a beefed up, slightly newer version of it. But look, they have almost the exact same buttons. They do the exact same things. This one, if you like technical details, just has more RAM and fancy stuff that makes it run faster. But the 83 is still a wonderful calculator. These are the kind of gold standard, in my opinion, for graphing calculators. They do a lot without doing too much, meaning doing the work for you. The TI-89 graphing calculator, we're going to say no to that one, and as well as any the TI Inspires, unless you let me know personally, your situation or something. The problem is those calculators go a little above and beyond what we need. But this calculator, if you want to use a graphing calculator, I would suggest the TI-83 or the TI-84, and definitely not the rapper TI. That's my second rapper reference today. I'm pretty proud. Well, is Limp Bizkit rap? Because then that's been 3. So Fred Durst, huh? So yeah, that's what I would suggest getting for yourself. And obviously this one's going to run you more expensive. Now you might be able to find it on eBay, Craigslist, if you're willing to meet in a parking lot at night, which I've done that before. I bought, or my friend bought a video card off Craigslist like 10 years ago for his computer. And we met the guy in this random parking lot that was dark, but guess what? He was a totally nice person, and the transaction went down fine. It was just a little weird. It was a little weird. We were making jokes about it. Okay, so that's kind of my admonishment to y'all is go ahead and get you one of them 2 types of calculators. The TI-30, the scientific, is perfectly fine, and it's the cheaper option, and I ain't got no beef with it. But the 83 or 84 graphing calculators will go kind of above and beyond for you. Any questions on that right now before we hop into chapter 2 here? Any questions, comments, concerns? Let me pull up the chapter 2 material. And what we're going to find out is that with chapter 2, we are going to, again, chapter 2, though, will not require that calculator. I just wanted to give you like a week or so heads up before you'll really need that calculator heavily. Okay. Let's jump on into chapter 2 there. In chapter 2, we're going to be learning something called set theory. So I always have to make this joke. I apologize in advance. It's a really corny joke. Set theory, let's talk about sets. Yeah. You remember that song? Yeah, from the 90s. Oh boy, I think it was Salt and Pepper did that one. So yeah, let's talk about sets. It's not what you think it is. A set, if you think about a set of things just in, natural life, you might think about a collection of objects. Oh, actually, that's the exact definition they use. That was just a coincidence. A collection of objects, and specifically whose contents can be clearly determined. So no mystery box nonsense where you don't know what's in the box. We're talking about a set. We're going to be pretty explicit about what the elements of the set are. Elements are the members of the set. They are the objects that are physically in the set. And our set must be well defined, meaning that its contents can be clearly determined. That doesn't mean we're going to list out every object or element in the set. We can have something called an infinite set. We can have something called an infinite set, which is exactly what it sounds like. It is a set that contains an infinite number of objects in it. Think about the natural numbers, the positive whole numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. The natural numbers are definitely an infinite set because there's no largest natural number. It can keep rolling. You can keep going higher and higher with that. So there's an infinite number of things. Here, I'll even write it out. And I know I might be getting a little ahead of myself. And again, I apologize for the Limp Bizkit jokes. Maybe you're like, Mr. Gunther, I'm a huge fan of Limp Bizkit. How dare you make fun of them? And I'm going to say, well, I am too, but I still understand that I was listening to that music when I was 11. So, Remember the natural numbers or the positive whole numbers? I'm going to share with you the actual set bracket that you should be using. This is the prim and proper way to write out a set. Notice that nice bracket. It looks like I don't know, calipers or something that are open. That is the proper set bracket, and that's proper notation. The way I did it was I said, who's got time for the proper? I'm just going to put some squiggly lines, all right? That's going to be the way I write it because, oh gosh, I have to do this every time. And that's my best. I mean, let's see, curve it, and I mean, it should be curved even here. And even that doesn't look good. That kind of looks like a face or something. But that's as good as it gets. Not the Jack Nicholson movie, but when it comes to my handwriting, you're just going to have to live with it, folks. But anyways, so that's going to be the proper set bracket, but I'm going to use squiggly lines. But anyway, any rate, we still need to know what the elements in the set are. Even if it's infinitely large, we have a conception of what it is. The natural numbers, we know exactly what the natural numbers are, even if we don't list out every single one. The order in which the elements of the set are listed is not important. That's technically true, but generally that doesn't mean you don't want to order them. It just means that two sets are equal even if you reorder them. If you change the order, like so if I put the natural numbers were 2, 3, 4, 1, then 5, 6, 7, 8, 9, 10, and it just kept going. Okay, I've reordered them, but like it's the same set. So it doesn't matter. It's like if someone hands you a bunch of bills, they hand you a 20, a 5, and a 10. No matter what, that's $35, whether the $20 bill was on top or if the $5 bill was on top or the $10 bill. Doesn't matter the order you received the cash, it's still $35 total dollars, which is what you really care about. So technically I can reorder the elements in a set and have the exact same set. This table is so squeaky. So let's talk about a distinction. There are the elements of the set, but then the set itself can have a label. So let me just show you kind of what I'm talking about. Notice here for the natural numbers, this is the set, including the brackets. You have to include the brackets. That's part of the set. These are the things inside the set, but the overall set itself has this label, this weird N, which I'll draw a little bit better here using the line tool. Remember, it was this weird N. Something like that. Think of it like this. Your box of decorations, of your Christmas decorations that you're probably about to whip out and start putting them up this year. Your box of decorations, the decorations are the elements of the set, but the set is the entire thing. It's the box with the things in them. So these brackets here, the open bracket and the closed bracket, are kind of like the box. And then the things in them are just part of the set, but the entire set can have a label. So you can put the label Christmas decorations on your box. In math, the labels that we use are usually going to be capital letters. That's not strictly required, but usually you'll say, oh, this is the set W, capital W. So W in this case is the set of all days of the week, Monday through Sunday. Why did they use W? I have no idea. They could have used a capital D for days, or okay, W for week. Okay, I guess I see that. All the days in a week. Okay, that's fair. There's a couple different ways that you can represent a set. The first way is to just use a word description. But this is PowerPoint, but it's still a word description, not a PowerPoint description. That's just a little Microsoft Office humor that's going down. If you didn't understand that joke, you didn't miss anything. It wasn't funny. A word description is simply literally what it sounds like. You just say, capital W is the set of the days in a week. And you don't have to list out the set itself. If it's clear what you mean by the set of days of the week, then you're good to go. The kind of more exact way or clearer way is to use the roster method, which is to literally just list out the elements of the set. It's just to list out the elements of the set, Monday, Tuesday, Wednesday. You make it a comma-separated list. You open and you close that set bracket. Don't you think about forgetting those set brackets. Those set brackets are your life when it comes to set theory. Otherwise, I have no idea what you're talking about. So you use them set brackets there, huh? There's going to be, you can still use the roster method for an infinitely large set. I keep going back to the natural numbers. This here is still the roster method because I'm listing out the elements in a comma-separated list, and I've at least established the pattern for what comes next and how the set looks going forward. So I would still say that, yeah, that's still the roster method. Totally fine. You think of a roster, you think about like a basketball team, and you just think about the players on the team. So you just think about the roster is just a listing of the elements or a listing of the parts and objects in the set. So yeah, here's a word description of the set. The set is capital P, Washington, Adams, Jefferson, Madison, Monroe. So the set, capital P, is the set of the first 5 presidents of the United States. So here is the roster way of representing that, and it's just their last names. And it's extra confusing because the next president would have been another Adams, wouldn't it? It would have been John Quincy Adams, John Adams' son. And so we're going to see that that actually gets us into some sticky trouble because repeated elements in a set are not necessary. If I see Adams twice in the set, I throw out the second one, except in this particular case, that's really, they are 2 different men. This was regular John Adams. This was his son, John Quincy Adams. So then I wouldn't throw them out. So that's kind of why they stopped at President 5, Monroe. But anyways, boom, you have a comma separated list listing out the elements of the set. That's the roster method. You have a verbal description. It's the first 5 president. Bada bing, bada boom, nothing too wild going on. But again, we're about to introduce some things that are going to be a little bit more kind of, challenging or difficult maybe. Right, using the roster method. So the verbal description, set capital C is the set of US coins with a value of strictly less than $1. Expressing this set with roster notation, you'd say capital C equals, you can use an equal sign. This is the set. Open your bracket, and it looks like they're in order from lowest to greatest value. Penny, a nickel, a dime, a quarter, a $half. There might be, I think there was a 75-cent piece. Some coin lover probably could lecture for 3 hours about the 75-cent piece. And you know what? That might be the one topic that will bore you more than math. So, hey, math's not the most boring topic out there. A 3-hour lecture on the 75-cent piece might just be that. I think there was I don't think there's been any other pieces. So that's going to be it. But again, this doesn't have to be in order. If it just makes sense to put it in order. And if you have OCD, maybe you're going to hate what I'm about to do, but you could put them all kinds of different places. Dime, penny, nickel, $half, quarter. It's the exact same set. It doesn't matter the order of the objects you have in there. So that is somewhat interesting. But again, you're just like, no, please just put it in order. You're killing me, Smalls. That's kind of what's going on with that. So those are the first two, kind of the principal two ways of notating a set or of explaining what its elements are. You can either literally write them out, or you can give me a description of what they should be. Finally, you can use something called set builder notation. Set builder notation, which is where you share some kind of formulation for what the set is. You tell me this is either it's either a formula or it's just some kind of mathy looking way of expressing the elements in the set. So here you might say set W is, the equal sign means is, the set of, the bracket means you're talking about a set, all X, all elements X, such that vertical bar means such that X is a day of the week. So read quickly, capital W, W is the set of all elements X, such that X is a day of the week. It's the set of all days of the week. Now you might say, why would you write it like this? Why wouldn't you just either write it out verbally as a word description or just write Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday? It's because this is actually a little bit more concise, isn't it? If I just write this, it's a little bit more concise. I don't have to write out as much. Remember, the word description was a little bit, and it's not precise looking. It doesn't use set brackets. So the word descriptions are nice, but set builder notation is usually the quickest way to write out a set, unless it's a really small set with only like 3 elements. Another thing to realize is that a set doesn't have to have any kind of pattern or magical connection between the elements at all. So far it has, but I mean, you can have a set. You can have a set that looks like this. Call it the set F, and it can be the number 1, but then it can be the letter A, the letter Q, I don't know, an asterisk. I guess a set is nothing more than a collection of objects. It doesn't matter if there's any connection between the objects. Here, I would argue there really isn't a connection that's worth pondering about. There's just 4 kind of seemingly random objects, but this still is a set. It still is. There really is no way to express this set using set builder notation, because set builder notation kind of implies that there's a pattern or a connection between the elements or a way of generating all the elements. So far you might be thinking, well, this stuff's pretty straightforward, and I agree, and I think overall it is straightforward. But of course, things can get a little bit more complicated, and you have to think about things in a different manner. So for instance, here is the set A. The set A, it's all X such that X is a month that begins with the letter M. The word description is it's the set of all months that begin with the letter M. In roster notation, you would literally just write A equals March, comma, May. Did we miss any? I don't think so. Those are both of the M months. So it's just kind of a connection between roster method, things like that, word description, and set builder notation. Okay, so let's pause real quick. Let's take a quick pause here and say, okay, this is a good point to take a little mental break. We're talking about sets. The next thing we're going to talk about is something called the empty set. But the empty set is still itself a set and is still itself an object. So let's just define it. The empty set, also called the null set, or we'll call it empty, is the set that contains no elements. Element skateboards or otherwise, or just any other brand of skateboard. So it's the set that contains no elements. So this is kind of the sarcastic way of writing it, but it is accurate. You just open a set bracket, you look around and say, there's nothing in here. Then you close the set bracket. And that's it. That's the empty set. Now, again, this is kind of sarcastic. It's a little snarky. That is accurate, but this is the more widely used, I should say, notation for the empty set. I just kind of write it quick like that. Boom, empty set. You can imagine there's a ghost behind there that's getting blocked out by the Ghostbusters. And so the empty set is literally the set that contains nothing in it. Here's a verbal description. Here's a word description of the empty set. You can get real creative. The set of all numbers less than 4 and also greater than 10. Is there any number that is both less than 4 and also greater than 10? 3 is less than 4, but it ain't greater than 10. No, it doesn't make sense. There's no number which is both smaller than 4 and also larger than 10. That doesn't make sense. So that's actually a word description of the empty set, because then this is a set that has nothing in it. But again, let me stress, the empty set is still itself an object. The empty set is not the number 0. It looks like a 0, but it's not. It is a set which is itself an object that has nothing in it. It's like your Christmas decoration box on December 24th. That thing better be empty because all your decorations better be out celebrating Christmas. Or if you don't celebrate Christmas, that's fine. I'm just talking about what I'm going to do. We actually have some of our Christmas decorations up from last year. Above our fireplace, we still have like a little snow village with like Santa Claus and all that in there because we just like the way it looked, I guarantee it. So, but think about your Christmas decoration box on December 24th. If you used all your decorations, that box is empty, isn't it? But there is still a physical box that is your Christmas decoration box. And so the empty set is still an object. It's just an object that has nothing in it. It's not the same as the number 0. So be careful. Sets are not numbers. Sets can have numbers in them, but the set itself is not a number. It's like its own brand new mathematical object that you may not have worked with before. A number is something completely different. Another example of the empty set, all X such that X is a fawn that speaks. So they're saying there are no fawns that speak. Obviously, they've never seen Bambi, and that means that they are criminals. But I guess if we're playing the reality game, which is not fun, I guess there aren't any fawns that like speak a human language like English, but they still can communicate to each other in some way. They have different ways of doing it. But yeah, I guess there are no speaking fawns, so this would be an empty set. So this is pretty cool. It's kind of an abstract way to think about it. This is an important difference, important recognition to make. Which of the following is the empty set? This is a set that contains the number 0 in it. Wait a minute, that's not the empty set. This is a set that has one thing in it. In order to be the empty set, it has to have nothing in it. But instead, it's got something right up in there. So this is not the empty set. Don't let it fool you. This is a set that has an object in it. So this is not the empty set. We already talked about this one, just the number 0 by itself. It can't be the empty set because it's not even a set to begin with. It is a number that is 0. Now, in spirit, both of them kind of represent similar things. The empty set represents nothingness in a way. The number 0 represents nothingness, but in its own way, numerically or quantitatively nothingness. A set, though, is just a different kind of object. So again, this can actually be a little bit confusing. But the empty set is itself an object. This one that we already went through, all x such as x is a number less than 4 or greater than 10. We put a spin on it. Earlier it said and. This time it says the word or, completely different word. Are there numbers that are less than 4 or greater than 10? Sure. The number 1, it's less than 4 or it's greater than 10 because it's at least the first one. The number 13, it may not be less than 4, but it's greater than 10. So it's at least one of those two things, thus it's empty. So this set actually has an infinite number of things in it. This is actually an infinite set. You can think of many numbers very quickly that fit at least one of these two bills. There won't be any numbers that fit both bills, but that's okay. The word or is more inclusive. Finally, all x such that x is a square with 3 sides. Clearly that's the empty set because just by definition, a square has 4 sides. And you can't try to split hairs and say, I define a square to be something else. No postmodern nonsense in this room. This is a math class, all right? We have rigid, strict definitions of things and we stick to them, all right? Keep your postmodernism at your art museums. All right. So, yes, those are some empty sets. So we'll get into this. Let's take our little break, but first let me take attendance. So we've been talking about set theory. That's the name for this general concept that we're on today. So let's talk about what it means to be a member of a set. We're going to use special symbols to say that a certain object is an element of. So here's that symbol. It looks like an elongated capital E, which is actually the name of my band, elongated capital E. So whenever you use it, you're saying this is an element of. It literally means is an element of. If I use an elongated E and I cross through it like that down there, that means is not an element of. Just like equals and not equals, that kind of business going on. So it's a pretty straightforward object. It's really kind of useful. So there's a few ways we can use it. The letter R is an element of the set of ABC, blah, 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 all the way to Z. So it's implied that this is all 26 lowercase letters of the alphabet. So that would be a true statement because R is indeed an element of that set. 7 is not an element of the set 1, 2, 3, 4, 5. Well, that's a true statement. 7 is not an element of 1, 2, 3, 4, 5. Now, this next one is going to be kind of splitting hairs. This is saying the set A is an element of the set with the elements A comma B. That's actually going to be false. Because if you put set brackets around something, it itself becomes a set and is an object in and of itself. So here, A is just an element of this set, but here, A is the only element of an entire set. So they're not, it's just not quite clicking. Now, if you wrote this, just to be extra confusing, this now becomes a true statement. The set containing A is an element of a set whose two objects are the set containing A and then just the object B. It's a little bit splitting hairs, to be completely blunt. We're splitting hairs just a wee little bit. And we usually don't get that granular with it, but you might see it. And now we've already talked about the set of natural numbers. We're experts on the set of natural numbers. It's just the positive integers. We know exactly what it is. There's n, I guess if you zoom in, maybe you can see it. No, they use a slightly different script n in this font than we do. So we're just going to appeal to the natural numbers because it's going to give us a useful way of writing out certain sets. Set A is the set of natural numbers less than 5. Oh, so it's just got to be 1, 2, 3, 4. Because it's got to be strictly less than 5. 0 is not natural. No negative numbers are natural. So it's just the set of numbers 1, 2, 3, 4. If I change this from natural to real numbers, that suddenly becomes an infinite set. It can go all the way down to the negatives. It includes 0. Also, it can include weird numbers in between two natural numbers, or weird like negative 1.57824, something like that. So if you're talking real numbers, you got an infinite set right there. But if you're talking about natural numbers, you can only have 4 possible natural numbers that are less than 5. So this is a finite set with only 4 elements in it. Set B is the set of natural numbers greater than or equal to 25. This is an infinite set. It goes as low as 25 and then just keeps rolling, keeps going upwards all the way theoretically to positive infinity. This next set, set E, is all x such that x is an element of the natural numbers and x is even. In other words, all values that are all even natural numbers. So it's 2, 4, 6, 8, who do we appreciate? And then it goes 10, 12, 14, 16, 18, 20, and it keeps going forever because there's no greatest even number either. So they can use this element symbol even inside of set builder notation. And you just got to live with it. You got to deal with it. So we might use inequality notation with sets. Assuming you're restricting yourself to the set of natural numbers, all x values less than a would be your way of dealing with that. That's the way you can say it just kind of in usual math terms. But in each case, we're going to assume that x is still a natural number, which is kind of funky because normally we just assume x is a real number. That's the usual assumption. But no, here we're going to assume x to be a natural number. So for instance, all x less than 4, you could write that in set builder, all natural numbers less than 4 there, Pilgrim. That's going to be 1, 2, 3. You can't go any lower than 1 and be a natural number. So notice this is less than 4, so it doesn't include 4. This next one is less than or equal to 4, so it does include 4 in this case. Don't let that throw you off. But we've already talked about that. We've talked in detail about inequality notation. Greater than, all x values greater than 4 that are still natural numbers. 5, 6, 7, 8, etc., etc., etc. All x values greater than or equal to 4, but still natural. So now we can include the 4, 4, 5, 6, 7, and then it keeps going forever and ever and ever. It's an infinite set. You can even sandwich values. You can sandwich things. You can put them in between two numbers. X is in between A and B, and it's strict inequalities here. So all x values greater than 4 but less than 8 that are still natural numbers. The only numbers then are 5, 6, 7. You can't include 4, you can't include 8. If you do include the endpoints, all x greater than or equal to 4 but less than or equal to 8, but still a natural number, then that would include the 4 and the 8 as well as the 5, 6, 7. And then you can do mixed intervals. You can have an or equal to on just the first thing, but not the second one. So we'd include the 4, but not the 8. Here you have the or equal to on the 8, but not the 4. So it's 5, 6, 7, 8. Oh. So representing sets of natural numbers. Well, all x such that x is an element of the naturals, that x is a natural number, and x is less than or equal to 100. So you can go as low as 1, and then you can climb your way on up to 100. You can include 100 because it's the or equal to. But then once you get to 100, you better stop there, Pilgrim. The next one, all natural numbers that are greater than or equal to 70 but less than 100. You can go as low as 70. You can include 70, and then you're climbing up to 100, but you can't include 100 itself. So you got to stop at 99. So that would be that set written out in roster notation. And even in roster, we're going to use ... ellipses points to say just follow the same pattern in between, because it's just more concise that way. Now we're going to introduce a new term. This term is so confusing that I usually don't call it that. They're going to call it the cardinality, the cardinal number of a set. And it makes you think of, like, is it part of the Catholic Church, or is it like a red bird? No, the cardinal number is just a fancy way of saying the number of elements in a set. And we notate that N of A. The number of things in a set. N for number, we put A in there. We put parentheses around it to say we're kind of like we're doing something to A. We're counting its elements. So if you can't remember that that's called the cardinal number or the cardinality, don't sweat. Just remember this N of A terminology means I'm counting up the number of things in the set A. It's kind of like function notation, like f of x, something like that. One thing to note is that if you do for some reason have a set that has repeated elements in it, that has the same element showing up multiple times, a set only needs one thing in it to represent it. So if you have a set of numbers that are like 1, 2, 3, 4, 4, 4, 4, 4, 4, 4, and then 5, you can throw out all the 4s except one of them because you only need one representation of the 4 in that set. So the Christmas box decoration or whatever doesn't quite make sense here, because you can have two objects in your Christmas decoration box that are the same, but like two ornaments on the tree that are exactly the same, just two generic red ornaments that you plan to put in different places of the tree. So here, no, we don't do that. If there's multiple repeated elements in the set, you ignore them. You can even cross them out and exclude them. So when you're counting the number of things in a set, you're really only counting the number of unique things in the set or different things. So a simple example, find the cardinal number or just count the number of things that are in each set. The set A has the numbers 7, 9, 11, and 13. So the number of things in A is 4. There's 1, 2, 3, 4 different things in the set A. The set B down here, this is not the empty set. This is not the empty set. Don't be confused there, Pilgrim. That's not the empty set. That is the set that has the number 0 in it. So this set has one element in it. So the number of things in B is equal to 1. Down here, the set C, unfortunately, I have to make a really corny joke. How many of you are ready to hear me make that joke? You want to hear it, Madeline? Who out there in the Zoomosphere wants to hear me make a really corny joke? A really bad joke. Please, if I get 10 likes, I don't know. I would just, you want to hear the joke, Nikki? All right. I apologize in advance. I'm bringing set C back. I appreciate the kind LOL. I don't know if it was an enthusiastic LOL, but I appreciate it nonetheless. Yeah, I'm bringing set C back, and that's all I'm going to say about that joke. That joke can go ahead and die a slow or quick, painless death, I guess. Not slow. All right. So you have the set C that has the numbers 13, 14, 15, all the way up to the number 23. It's pretty clear that they're meant to all be natural numbers. You're tempted to say there's 10 things in this set because 23 minus 13 is 10, but you're actually wrong. What you don't realize is when you subtract, you're counting the number of spaces in between. So when I subtract 14 minus 13, I'm only counting the space in between 14 and 13, if you will. Exactly, but between 13 and 14, there's actually two numbers there. Between 13 and 15, if I do 15 minus 13, I'm just counting the number of spaces, the number of times I jumped to get from 13 to 15. So you think there's two, but there's actually three numbers there because the endpoints are there. So there's a general rule. If you read pages 67 through 79 in your book, you subtract, but then you add 1 to it. That's actually a kind of a somewhat famous rule called the N+1 rule, something like that. You might have seen it heard. So actually between 13 and 23, there's actually 23 minus 13 is 10, but there's actually one more than that just because of what you're really counting when you subtract. And so there's 11 objects in set C. The next thing we'll talk about, I don't go into uber detail about equivalent sets. It's not super important to me. We'll call two sets equivalent, which is a kind of a bad word for it. You'd think that two sets are equivalent if they're the exact same thing. If one set and the other set have the exact same elements in them, no more, no less, once you throw out repeats. But that's actually not true. For some reason, the sets are called equivalent only if they have the same number of elements. So you could have the set containing the first four letters of the alphabet, A, B, C, D. You could have the set containing the first four natural numbers, 1, 2, 3, 4. Even though those are completely different elements, they're called equivalent because they both have four things in them. They both have a cardinality of 4. Kind of, I don't like that word. That's why I kind of gloss over it. Equivalent, I guess I see it, but it's not super helpful. There might be some higher level math reasons for that, but for our purposes, calling them equivalent seems a little silly. But look, here you go. The set all X, such that X is a vowel, which is the set A, E, I, O, U, is actually equivalent to the set B, where X is a natural number between 3 and 7 inclusive, because that has 5 elements in it as well. A, E, I, O, U has 5 elements. 3, 4, 5, 6, 7, that's 5 elements. That to me, yeah, that's true. So all we're saying is that A and B are the same because the number of, or rather are equivalent because the number of things in A is equal to 5, the number of things in B is equal to 5. Let's not get too horribly hung up on that, but that is, I guess, technically one of those things that's true. Yeah, okay, maybe I can see why. They talk about one-to-one correspondence. We're not going to go uber detailed into that either. And it doesn't even really make a lot of sense when you compare it to the algebraic term of being one-to-one. Kind of. So don't worry too much about that. We can kind of gloss over this as well. You can kind of see why you want to make a one-to-one correspondence, because you might want to link every one element in one set to an element in another, just kind of arbitrarily assign something to it. But you can't do it in this case because this set B only has 4 things in it. This set A has 5 things in it. And one of those things happens to be the greatest thing in the entire galaxy. That's the United States of America. So you can't make a one-to-one correspondence because you couldn't assign each of these their own unique element from the other set. But well, yeah, I guess that's true. That's somewhat interesting in algebra, but we're just not going to be uber worried about it at the moment. Finally, we'll talk about what it means to be a finite set. It's exactly what it sounds like. It's almost better to define an infinite set. An infinite set is a set that has an infinite number of objects in it. A finite set is a set that has a finite number of objects in it. So for it to be a finite set, it has to have 0, 1, 2, 3, 4, 5, or so on. It has to have a finite number of objects in it. You can assign a natural number or 0 to express the cardinality of the set, the number of things in it. An infinite set, not so much. The best example of infinite set that we've been dealing with so far is the natural numbers themselves, which is why this is confusing, because you kind of see they're talking about natural numbers for a finite set, but the natural number set itself is an infinite set. You know, it's kind of like crazy. So don't think too heavily into their definition here. Just tell yourself, finite set has a finite number of objects in it. Even if it's 10 trillion objects, that's still finite. An infinite set has an infinite amount of objects in it. It never stops. It goes on and on and on and on. It is the champion. Equal sets. Now we're cooking with oil or playing with fire. I don't know, whatever the old term is. Equal sets are exactly what it sounds like it should be. 2 sets are equal if they have the exact same elements, once you throw out any repeated elements. So 2 sets are equal if they have the exact same elements. So 2 sets are equal. They're certainly equivalent if they're equal, because if they're equal, they're the same set, they're going to have the same number of objects, so they're also equivalent. But being equal goes one step further and says, not only do they have to have the same number of elements, they also have to have the exact same elements themselves. So again, equal sets, that's a little more interesting, or a little bit more along the lines of what we'll talk about here. So the set 4, 8, 9 is equal to the set 8, 9, 4, yeah, because they have the exact same elements, even if they're in a different order, that doesn't matter. In fact, they're equal to this set as well. If I throw an extra 8 into this set, well, that's a repeat. We already had an 8 in there. So I can ignore it. There's only 3 elements in this set. because the 8 is just showing itself again for some reason. But the proper notation, you would never have a repeat in a set in proper mathematical terms. But down here, the set containing 1, 3, 5 is certainly not equal to the set containing 0, 1, 3, 5. This thing has one element too many. It's got one extra thing that this doesn't. And it's not a repeat or anything, so we can't just throw it out. Okay, let's start real quick on the next section. Let me pull it up. We're going to talk about subsets. Subsets. What does it mean for one set to be a subset of another? Well, let's find out today. So, set A is a subset of set B expressed with this thing. It looks kind of like the less than or equal to symbol, but it's not. It's more curved. It looks like a magnet on its side, or a magnemite. Set A is a subset of set B expressed this way. If every element in set A is also an element in set B. The other way around doesn't have to be true. So if A is just the vowels, if capital A is the set of all vowels, B is the set of all letters, period, A would be a subset of B because all the vowels are certainly found in this larger set, but that would actually be called a strict subset or a proper subset. If you cross out the subset symbol, you're saying not. Just like if you cross out an equal sign, you're saying not equal to. It's the exact same idea. So the notation A is not a subset of B means A is not a subset of B. And look, the whole reason we use symbols in math is because I gotta say all that. A is not a subset of B. I can write that out much more concisely by just writing that. And I'm done, and I'm having fun in the sun. Set A is not a subset of set B if there is at least one element of A that is not an element of B. Okay, that's cool. One kind of weird, neat little result of this, I should say, is that every set is actually a subset of itself. Every set is a subset of itself. So for instance, if you take the set with the first 4 letters of the alphabet, A, B, C, D, that is a subset of itself because A, B, C, D are found in both sets. It's kind of weird. Let's look at an example. So the set containing the first, let's just say the first 4 natural numbers is a subset of the set containing the first 7 natural numbers. This is a true statement because all elements found in this set can also be found in this second set. Even though the second one is bigger, that's okay. It's a subset. The word sub makes you think of being a smaller than or being a minuscule or lesser version of. So this is a true statement. Another true statement, the set of the first 4 natural numbers is a subset of the natural numbers altogether. Because every value, every element of this first set is found in the greater set of natural numbers. 2 is in there, 3 is in there, 4 is in there. So if this first thing is a subset of that, that means all the elements of this one were picked from this larger set. That's the only place you can throw that in there. But if I try to throw pi into the mix, if I try to throw pi, suddenly, that's false. This is no longer a subset of the natural numbers, because for it to be a subset, every element of this had to have been picked from this larger set, from this natural number set, which is not the case here. But this would still be a subset of the real numbers. What's interesting then is, from what I was saying earlier, every set is automatically a subset of itself. Look, I've recreated the same set, but every set, every element here can also be found here. 2 can also be found here. 3 can also be found here. 4 can also be found here. So that's why it's kind of like the less than or equal to sign, but not exactly. It's because this is the or equal to case. If the two sets happen to be exactly the same, or that just means every set is a subset of itself, which is very wordy, but it is a true statement. So just some kind of interesting implications. Okay, we're going to either write is a subset of, or we're going to write is not a subset of to form a true statement. So let's say you have the set A is the numbers 1, 3, 5, 7 collected together. B is the set of numbers 1, 3, 5, 7, 9, 11. A then is a subset of B, because all elements in A can also be found in B. That's where my pickings came from. I only picked elements of B to be in this subset here, A. Down here, A is the set of all elements such that all letters of the word proof, basically. So P, R, O, and F would be that set. You're exactly right. So right now, as it's written, this is supposed to be a B. As it's written right now, A is not a subset of B, because A contains elements that B does not. But the other way around would be true. You are absolutely right. And I'm sorry, it's not showing up on Zoom. I apologize. Sorry about that, folks. Let me bring that up. So like we said, A is a subset of B here because 1, 3, 5, 7 could all have been picked from this other set B. But here, all X, such that X is a letter in the word proof, this is the set of elements just containing P, R, O, and F. And you don't need both O's because that's redundant. B is a letter in the word roof. Well, A is not a subset of B. But like you said, Madeline, the other way around is true. B, however, is a subset of A in this case, for the reasons you said, because now all the elements in B can be found in A. So the other way, true. Thus, the subset symbol is not always 2 ways. You can't just flip the order of them and have the exact same thing. That's not how it works. Okay, so I think that is a good stopping point for today.